Thanks, Rajesh. So we'll move on to the second part. And before I move on, let me do a quick recap of what we discussed in the first part. Okay. So that if you have any questions, you can ask me. Okay. So the three main things we discussed. The first part was basically that uh, the independence number of a graph or the size of the maximum independent set and the chromatic number of the graph are hard to compute quantities, but they are important both from theoretical viewpoint and also from applied or practical viewpoints of designing algorithms to find. Right? The specific example that we had considered where this turns up is the following. You have an alphabet. Um, in fact, let me not discuss the information theory part, but just give it like this, that you have an alphabet maybe labeled as A, B, C, and so on. There can be any number of them. It's not particularly the English alphabet. And consider a graph where the vertices are actually these labeled by these alphabet, by each of the letters of this alphabet. Okay. And there's an edge if when you send this vertex, when you send some information over the channel that we have discussed, uh, the alphabet at vertex I and the alphabet at vertex J are liable to be confused. Okay. In that case, you put a conflict edge that I is conflicted with J, and this denotes that both of them cannot be transmitted together. So that was our motivation. Okay. And alpha of G is the maximum size subset of non-similar messages that you can send across. Okay, of the single alphabet messages. So we had then modeled, we had gone one step further and asked that suppose you are allowed k uses of the channel, right? And you consider instead of G, you consider G to the power k, whose vertices are V to the power k, and let me call it say E prime, right? Where there is a edge between in the graph GK between V1 to VK and V1 to VK prime. Let me call this V1 prime to VK prime. Right. There's an edge between these two if Vi is similar to Vi prime for all I. Okay, when I say similar, I mean either there's an edge in the original graph or Vi is equal to Vi prime. That is, they're the same vertex. Okay. And we had kind of motivated the definition of the following quantity, which we call the Shannon capacity, which is basically, I called it sigma of G, where not this quantity, we'll define it again soon. Okay, so we had considered the quantity alpha of G power K, which is the maximum independent set size in this graph G power K, right? And that is the maximum subset of non-similar messages that can be transmitted, but now in G power K. Okay, why are we doing this? Because the information, so-called information that you transmit per alphabet symbol is now logarithmic in that. Okay, so it's log of 1 over k log of alpha G power k. So we had given some motivation for this. If it was not very clear or you don't understand completely, it's fine. It's just that this quantity is an important one to consider. Okay, it gives an idea of how much information every symbol that you transmit is kind of giving. Okay. Now, coming to independent sets, one important thing was that the independent set in the product graph G power k is at least the size of the independent maximum independent set in the original graph raised to the power k. Okay, and we had seen that for the C5, the cycle on 5 vertices, this can be strict. Okay, so for C5 squared, the maximum independent set size was 5, which was larger than 2 squared, where 2 is, of course, the size of the maximum independent set in a cycle of size 5. Right? So this is a quick summary and recap of what we did. And now let's go ahead. I will give the definition of Shannon capacity again because it's important. Okay, and that's going to be the basis of what we're going to discuss here. Okay, so you take the graph, original graph G. Okay, you take the kth power of it in a product sense. Okay, we'll define it formally again when needed. Uh, and you take the supremum over all k being natural numbers of 1 over k log of the maximum independent set size in G power k. Okay. And this quantity we call the Shannon capacity. It's about the capacity of how much the channel can take for transmitting information per symbol. And we had mentioned that the sigma of G is bounded, and yeah, it satisfies the limit exists as k tends to infinity, and that is what the limit is sigma of G. Now let's pick up from where we ended, which is basically that the sigma of G is quite hard to compute, even for simple graphs. And after 20 years, Lovasz managed to determine the Shannon capacity of the phi cycle. Okay. And he did this using what we'll call a relaxation eventually in tomorrow's lecture. But for now, the term may not be very clear why I'm calling it a relaxation. Okay. So what we'll do now in this lecture is actually look at Lovasz's proof and look at how is sigma C phi shown, okay, how it is determined. Okay. In general, let's start one step back and say that, okay, let's take a general graph, and see how do you find sigma of G. Okay. It's hard to compute, right? It's hard to find. So just for convenience, we will take the exponential of sigma of G. Okay. So instead of taking 1 over k log of the maximum independent set size in G to the power k, we will take 2 raised to sigma of G, which is basically this quantity. Now, to give you some sense of scale, we know that this is at least alpha of G to the power of k whole to 1 over k. Notice that the k has moved out, right? So it's the maximum independent set in G power k is at least the maximum independent set size in G to the power k. And then I'm taking again a 1 over k of that. So this is at least alpha of G. Okay. This quantity I'm calling capital S of G. Okay. There's a slight departure from what is there in literature in terms of the notation, but this is easier to kind of explain. Okay. Yeah. So S of G, which is exponential of the Shannon capacity. So finding sigma of G is the same as finding capital S of G. Okay, they're basically the same quantity up to the power.
So the
So,
rightmost
yeah.
inequality will be equality.
So the last one is the equality. You're right. Sorry. Yeah. Thanks for pointing it out. Okay. So S of G, which is the quantity we are interested in, is at least alpha of G. Okay. And this is trivial. Nothing very interesting over here. But we want to kind of see how much is it always the same as alpha of G? And we saw an example for C phi, it will be larger, but how much larger, right? So the idea in all of this is that, well, S of G is a really hard quantity to kind of think about, right? You're taking a graph, you're taking its kth power, finding the maximum independent set in that kth powered graph, and then again taking raised to 1 over k. Right? So that kind of seems difficult to look at, but maybe there is a simpler quantity that that is more easier to analyze, and we can look to bound that instead. Okay. And Lovasz's idea is basically to look at some sort of a geometrical representation of G, okay, or some value that is derived from a geometrical representation of G, and then analyze that quantity's properties. Okay, let me loosely state it. Look at some version of a value of a geometrical representation of G. Okay. And what is the idea of this? I like this example to state this example. So here's your detective, say Sherlock Holmes, at a crime scene. And all of a sudden he looks around, and of course the criminal is not around at the scene anymore. But by looking at maybe the footmarks of the criminal, the size of the door, and other things around the crime scene, he kind of makes a clever estimate as to what the height of the criminal is and possibly even his identity. Okay, and that's basically this the geometrical representation that Lovasz gives. You should think of as these footprints that kind of guide you to what the actual value should be of S of G. Okay, okay, good. So now that that is clear, um, let us define what are these geometrical representation of graphs that Lovasz works with. Okay. So from now on, most likely, whenever I'm talking about a graph, its vertex set will be identified with 1 to n, at least the base graph, right? And I will call the complement, E complement, to be V choose 2, which is basically the set of all pairs ij such that I not equal to j minus E, okay, unordered pairs. Okay, so basically this is like the complement graph, okay, of G. Okay, if I look at E bar. So what is an orthonormal representation? Now, once I state this, it will look like it's coming out of thin air, but there is actually some motivation for it, and it will become clearer as the slides progress. So you're given a graph G, and you want to assign a vector for every vertex. Okay, set of unit vectors. And let me call the unit vectors u1 to un for the vertices 1 to n. Okay, so u1 is a vector assigned for v1 for vertex number 1. u2 is a vector assigned for vertex number 2, and so on. So for every vertex, you get this vector. Okay, and the constraint that we wanted to satisfy for it to be useful for us in analysis is basically that two vectors should be orthogonal if ij is in E bar. Okay, that is, there's no edge between I and j. Okay, again, any two vectors corresponding to vertex I and vertex j are to be orthogonal if ij is in E bar. Okay. Now, the first question you might be want to ask is, well, what is the dimension of these vectors? I have not quantified what space these vectors are lying in, right? So, can someone think of what should be the dimension or what dimension is sufficient?
Okay.
Well, I couldn't hear you in case someone spoke, but just let me keep the chat on so that if there are questions in the chat, I can take them. Yeah. Right. So what should the dimension be of these vectors? What ambient space should we consider these vectors to be in? Right. So one suggestion is to take the ambient dimension as k. Like these are vectors in R to the k. Right. Uh, well, we need something possibly more than that. Okay, so we need more likely because the number of constraints that are there should be satisfied between every pair of vectors, and there are n of them. Right? So let's just be safe and keep the dimension as n. Okay. Okay. Of course, it may turn out that some representations lie in a lower dimensional subspace of Rn. But that's fine. And you're looking at unit vectors, so all of them are basically lying on the unit sphere in n dimensions. It's a bad sphere, but yeah. So this is like, oops, sorry, Sn minus 1. So all the vectors lie in Sn minus 1. Okay. Good. Any questions about the definition of orthonormal representation? Yeah. Let's go over a few examples to kind of make this concrete. Okay. So first I claim that any graph you give me has a trivial orthonormal representation in Rn. Okay, recall that the condition is you need to assign a vector for every vertex such that ui transpose uj is equal to 0 if and only if ij is in E bar. So can someone tell me a trivial representation that is kind of works for all graphs? You just need to ensure that certain dot products are zero, that certain vectors are orthonormal, right?
If there is no edge in the graph, then we can take two linearly independent vectors corresponding to the vertices.
Mhm. So yes, you can do that. I mean, you can take linearly independent, but we want a bit more, right? We want them to be orthonormal, so they need to be orthogonal for all. So yeah, the suggestion in the chat Divesh has given is actually correct. Basically, what you do is just take the standard basis vectors. Okay, assign vertex I to just EI. Okay, EI is what? It's just this. Is a standard basis vector at the ith location. So this is kind of a trivial orthonormal representation because it's not just that the edges have got orthonormal vectors. Every pair of vectors are orthonormal. Okay, so it trivially satisfies the condition that we wanted to begin with, right? So this is fine. So now is this the end of it? Why was the orthonormal representation even defined? Okay, we'll come back to this in a moment. Till then, let us come up with something for the complete graph. Can someone suggest orthonormal representation for the complete graph? That is not the trivial one. So what would be a non-trivial orthonormal representation for the complete graph? Well, notice that the complete graph has a pair of edges has an edge between any pair of vertices, right? So basically, you have no constraints to satisfy at all, right? So what could you do? Well, you could take all the vectors to be the same, right? You get a one-dimensional orthonormal representation. Okay, you could maybe set it to be E1, right? Doesn't matter. Right? So here's a non-trivial orthonormal representation, and this works for the complete graph, but not for others. Right? And if you look at the opposite, which is the empty graph, then the trivial orthonormal representation is the only representation possible for that graph, okay? Because you want every pair to be orthonormal.
So in the case of complete graph, the
Mhm.
dimension will be one.
Yes, so you can set it, you can think of it as lying in Rn, but actually it's just a one-dimensional representation. So you could as well take the dimension to be one. Right? Okay. Good. So these are two extreme examples, maybe some non-trivial examples to kind of work. So here's a four cycle, right? Let me label the vertices 1, 2, 3, 4. Right. Now, can you give me a non-trivial orthonormal representation for C4? Can anyone suggest? So what do you want? You want vectors U1, U2, U3, U4 such that what are the conditions to ensure you want U1 is orthogonal to U2. All are unit vectors, so that you can always assume U3, U4, and U4 is orthogonal to U1. So the condition is for, so Shashwat's question on the chat is the condition for E bar? Oh, sorry, that's right. The condition is for E bar, my bad. Right. Yeah. So what would be a non-trivial orthonormal representation for C4? Well, you can do this just in 2 dimensions in case you're thinking about this. Why? Because there are only 2 orthonormality constraints, right? So that can always be satisfied in 2 dimensions. So just in the plane, can someone suggest me vectors which will do this? So take the origin, U1, and now I want U3 to be perpendicular to U1, and I want U2 to be perpendicular to U4. Okay, so the 2 edges that are not there, now they are satisfied using this constraint. Now, the same graph can have multiple orthonormal representations, which are equally valid. Okay, and they will be non-isomorphic. So notice that I'm drawing this, assuming maybe that this is my, oops, that this is my axis, right? But then any rotation of the vectors also gives me an equivalent orthonormal representation of the graph, right? And so if I rotate this in the plane or in any direction, the orthonormal vectors continue to remain orthonormal. It's basically you do a unitary transform, everything remains the same from the point of view of orthonormality constraints, right? So what would be a non-equivalent under unitary transformation representation for this cycle? Can someone think of some other representation? Well, one way is to just go 1 dimension higher, right? So suppose you go to 3 dimensions. Right. You could just make another constraint. You could just put the vectors. Say you put U1 and U2 together. And you put U3 and U4 here. Right, so it satisfies both. U1 inner product with U3 is 0, and U2 inner product with U4 is 0. Right. And both of these are not equivalent. Right. So there are multiple orthonormal representations possible for the same graph. And what we were looking for is some sort of efficient orthonormal representation. Okay. So
Sir,
what do I, yes, question?
but here U3 and U4 inner product will also be 0.
Yeah, but that doesn't matter, right? Because the only constraint that we want is these two to be satisfied. So for instance, if you take the trivial representation, then everything is orthonormal, right? So you can have extra things that it satisfies, but it should satisfy. These are the necessary conditions for which necessary and sufficient ones. If it satisfies, it's called an orthonormal representation. Okay.
Sir, can we explicitly write these vectors?
Can you write this? Sorry.
Explicitly write these vectors U1, U2, U3, U4.
Explicitly write these vectors. Well, it's not very difficult. You just take this, which if you want the second representation, right? So then you could just write this as maybe, suppose this is the x-axis. So it's just the standard basis vectors that I've used. Okay.
Okay, sir.
Okay, so I hope the example makes it clear what we are looking for. When you have more complicated graphs, you may have to look at more complicated ways of arranging these vectors. Okay, if you want a non-trivial representation. What we are looking for in particular is an orthonormal representation, which I'll mostly denote by OR. Oops, sorry. I want an orthonormal representation with low value, or that is efficient in some sense. Okay, so OR stands for orthonormal representation. So how do I define the value of an orthonormal representation? You're given a graph, and suppose someone has given you an orthonormal representation of it. Okay, this geometric representation of vectors for vertices. And now what you will do is you'll try to evaluate how good is this orthonormal representation by assigning a value to it. And the value of the orthonormal representation is defined as follows. It's a slightly complicated looking expression, but maybe if you evaluate it a couple of times, it'll become more clear. Okay. So there's a min and a max term. Let's go over these terms a bit more carefully. Okay. So the vector C, so you minimize over choices of a vector C that's not part of my original orthonormal representation set. Okay. So it's minimized over C, again unit vectors, such that you maximize the quantity 1 over C transpose Ui the whole squared. Okay, I'll let you stare at this for a few seconds so that kind of get used to what's happening. So for instance, let's try to evaluate this on a couple of things. Okay. So the vector C that you assign over here that minimizes this quantity is called the handle. Okay. So let's take the trivial representation maybe and start with that. Okay, what is the value of the trivial representation? And it doesn't matter what the underlying graph is because yeah, it could be any graph. Once you give once you give me a set of vectors, that is a OR for a graph, I just want to evaluate what is the minimum value over C of this quantity. Okay, by the way, one thing I should say is that this variable here is the small version of theta in case you're not used to it, and it's read as just theta. Okay, it's a cursive version so-called of the usual theta. Okay, good. So now let's do an example. So suppose I have the trivial orthonormal representation for a graph. Maybe it could be any graph because it's a valid orthonormal representation for any graph, right? So, so my vectors are E1, E2, so on until En, right? And if it's E1 to En, I have some ability to choose C. So recall that this theta of this representation was defined as choose a vector, unit vector C, whose all norms are two norms of the maximum over I in N of 1 over C transpose Ui whole squared. Okay. Now, for the trivial representation, what would be a natural choice for the vector C that minimizes this? Okay, think of C transpose Ui as the projection of C on Ui. The component along that, it's squared. Right? So now if I have these vectors, the standard basis vectors, and I want to minimize these dot products because I'm maximizing 1 over C transpose U, I kind of want to minimize it with everyone. Right, what would be a natural choice for the vector C that minimizes this? Let's just do 3 dimensions for simplicity, right? So notice that I want to, this maximize of 1 over the projections is like minimizing the projections, right? Now, if I put the vector C along any of these basis vectors, then although I make the projection on the other point 0, the projection along E1 goes up to 1, right? So I want to avoid that, right? So, and because this instance is so symmetric, ideally I should be taking C to be just, seems natural to take C to be 1. But how do I normalize it as? Maybe for 3 dimensions, it's just 1, 1, 1. But for n dimensions, it's all ones. But I should, I want it to be a unit vector, right? So I need to normalize it by square root n. Okay. Um, so this is a unit vector. So basically it points, somewhere like this. It's difficult to draw it in 2 dimensions, but you see it's basically, uh, yeah, the average of all of these scaled appropriately. Okay. And now you can compute what are these projections, right? And can someone work out quickly and tell me what is the value of this orthonormal representation? Yeah. So I will leave it as an exercise. By the way, I was not clear in the previous one when I said that if you take C to be along one of them, the projection along E1 goes up. But if you look at 1 over E2, so basically the projection on E2 and E3 goes to 0, right? Let me just write it here as a candidate. It will be useful to know. Then this becomes unbounded, right? So let me just write it very loosely. I know I should not do this, and it's basically undefined, right? So you need to kind of work around this by defining a small enough ball around these points and avoiding these singularities. Okay, so I'm not making that very formal over here, but I guess you can work that out yourself. Okay, so that's why you want to avoid these. And then the central point will give you what you want. Okay, good. Now, what about the other one for the complete graph, right? There was a easy representation for the complete graph. All vectors were the same. So you had like, say, all of them are U. Okay, this was a valid orthonormal representation. And now, what can you take C to be? That will minimize this. So what is the handle that, um, yeah, so this one is equal to N. Good. So what is the handle that will minimize this for the complete graph? Yeah. So if you take C equal to U, then max of 1 over C transpose Ui, all the Ui's are the same, is equal to 1, and therefore the value of this orthonormal representation is equal to 1. Okay, so here are two kind of opposite orthonormal representation, and they have certain values. As an exercise, I urge you to do the same for the other orthonormal representation that we did. Oh, sorry, this should be for the disconnected graph. Yeah, I keep messing up my E and E bar. No, this fine. This for the complete graph. Yeah, this is for Kn. The question was, is it for the complete graph or totally disconnected graph? This is a representation for the disconnected graph because the less the connections a graph have, the more constraints it has. Right. So there are no constraints on the complete graph because all edges are present. Good. Okay, so now that this is clear, as an exercise, work out the other orthonormal representation, the value of the orthonormal representation for C4 that we saw. And see what value does that give. Let's move on to the next part. Okay, so now, as you've seen, there are multiple possible orthonormal representations. Is my video stopped? Okay. Rajesh, am I audible? Yeah.
Yes, yes, you are audible and visible. Yeah.
Okay, thanks. So let's define theta function, which is basically the following. You're given a graph G. There are multiple orthonormal representations possible for it. Each gives different values, right? And now the theta function for a graph G is the value which is the value of the orthonormal representation, which gives the minimum value, right? So it's the minimum over U, which are orthonormal representations for G of theta of U. Okay. So for instance, for the complete graph, right, there were two possible orthonormal representations. There was the trivial one, and there was the one where all vectors are the same. Both are equally valid, but the one where all the vectors are the same is more efficient in some sense. Okay. Now, if you think of it in some way, here's a very intuitive kind of picture to keep in mind for understanding this. By the way, there are some technical conditions. I'll come to that later. But here's what. So intuitively, for some reason that may not be clear for now, what we want, all the vectors to kind of fit in the small spherical cap around the handle C. That is, if this is my handle C or optimal handle C, a good orthonormal representation will kind of keep the vectors near to C in some way. Okay, so that's the intuition. Okay. While of course you need to maintain the orthonormality constraint. So for the complete graph, all the vectors were the same, right? And it was ideal. That's because you had no constraints to satisfy. But you can imagine that as you have constraints to satisfy, these vectors should spread out around the handle so that kind of they become orthonormal. At least some of them become orthonormal. Okay, the ones that are not orthonormal, you can keep them at any angle relative to each other. The ones that are constrained should become orthonormal, so they need to spread out from that handle C in some way. Okay. Okay. Now there are some technical conditions. Why am I saying in both the cases when I define the value of an orthonormal representation, or for this, I called it a minimum, although the minimization was over like infinite subsets, right, of possibilities, an infinite subset of possibilities. And the reason is basically just that, all of the sets that you can consider are compact and the functions you consider are continuous. Okay, I'll not stress too much on this. You can kind of argue for yourself why this is the case. The set is compact because of orthonormal representations is compact because if you look at the closed sets of ui transpose uj equal to 0 being the constraints, and you're intersecting that with Sn minus 1, uh, right? Sn minus 1 to the power n. Roughly. So then both are compact, and so it's fine. Okay. Now I've defined this quantity theta of g, right? And now, hopefully you have some idea of what it is, right? And the question is, why should we consider this at all? So remember what I told you, theta of g is kind of our footprints in the mud that is giving us some idea of what the actual thing that we are after, the Shannon capacity, should look like, right? So that's the idea. And let's go ahead and actually, Lovasz actually showed this. This is the following. S of g, if you remember, S of g is the exponential of the Shannon capacity, right? So this is what? This is just, I'll just write it in terms of graph theoretic terms without any reference to information transmission. This was just the kth power of g, the maximum independent set in that, raised to 1 over. Sorry, there seems to be some issue. Yeah. Right. So S of g was the size of the maximum independent set in the kth power of the graph, okay, raised to 1 over k. Right? And the main theorem that is going to be of use to us is that the quantity I defined below, this geometric representation, right, and its value. So the optimal geometric representation has a value that is at least the quantity that we are after, okay, which is this alpha of gk raised to 1 over k. I'll stop for a moment. This is a key theorem and we are going to prove this. Okay. If you have any questions, please let me know. Okay. So the proof is basically divided into two parts, both of which individually are not very difficult to show. Okay. The first part, which we'll call lemma A, is basically the following, that if you have the um, theta function of a product of two graphs, right? The claim is that it is less than equal to the theta function of g times the theta function of h. Okay. So in particular, if you take h to be g power k minus 1, then you get the corollary which we'll use. Okay. So you're given a graph g, you're given a graph h, and you look at the theta function value of g dot h. Okay, what is g dot h? I've not defined it formally, but you can think that, the vertex set of g dot h is going to be what? It's going to be the Cartesian product of the vertex set of g times the vertex set of h, right? And there'll be an edge if the relative, each coordinate is similar. Okay. We'll define this more formally later, but you do know the quantity g power k, right? And as a corollary, it gives us that the theta function of g power k is at most the theta function of g whole power k. And this part we'll use, because notice that we are thinking of it as difficult to get a handle on alpha of g power k. And what we are doing is basically saying, well, I can't handle alpha g power k easily. Let me go after this theta function. Okay. And now once I know that theta function has this nice multiplicative kind of property, I relate theta function back to the alpha function. Okay. And lemma B basically does this. It states that for all graphs G, the size of the maximum independent set in the graph is at most the theta function of the graph. Okay. So before I go to show these two lemmas, it will not take more than 15-20 minutes of time. Uh, how are we doing on time? Yeah, we should be fine. Yeah. So before I go to prove these lemmas, let me just use these two lemmas to show the theorem. That's really easy. Okay. So what should I first do? Can someone suggest to me what I should first do with this? I have the corollary in hand, the multiplicativity of the theta function, right, under graph products. So notice what I'm going to do first is actually use lemma B and apply lemma B on G prime being G to the power K. Okay, fix any K. So I'm going to use lemma A and lemma B to prove the theorem above. Right. When I apply this, what do I get? Alpha of g power k, which is basically the quantity we are interested in up to this 1 over kth power, is at most theta of g power k. Right? And while alpha of g power k, we could not easily relate it back to alpha of g. If we are done, then we would directly have a bound over there, or we'd have directly know what is the Shannon capacity there. The theta function we can kind of work with. So this is lemma A, this sorry, lemma B. Okay, and this is lemma A. The second inequality is from lemma A. Okay. And now what do? I just take the left side, the two extreme sides of this inequality, and infer that alpha of g to the power k whole raised to 1 over k is less than the theta function of g. Okay, good. I hope this is clear. Okay, I just applied lemma A and lemma B. Okay, again, the key takeaway here is that theta function of g has this nice multiplicative property that is very easy for us to handle in terms of graph powers, whereas my alpha g, the independent set size, did not have this. And the left-hand side is just S of g. Okay, so this finishes the proof of the theorem, assuming the two lemmas. So now what we have reduced showing the theorem to is just showing what these theta functions or properties of the theta function, both lemma A and lemma B are basically properties of the theta function. So let's go ahead and show these. Okay, so this will require some work, but not too much. Okay. Okay, so let's start with defining this strong graph product G dot H. It is intuitively the same product that we used when we considered G power K, right? So if you had this notion of similarity, let us say G, let me write it again over here. H is W comma F, right? And if H is W comma F, what do we do next? Well, the strong product graph between G and H is defined as follows. So the vertex set is what you would expect is V cross W. And there's an edge VW and V prime W prime if, okay, can someone suggest what the definition should be? It's basically what we have seen all along. If V is similar to V prime and W is similar to W prime. When I say similar, it means either there's an edge in the base graph, either G or H, depending on the coordinate, or both are the same vertex. Okay. So this is in G and this will be in H. Okay, so in the base graph G, two vertices, or in any graph G, we call two vertices similar if they either are the same vertex or they have an edge between them. Okay, good. So actually one thing I should say here is that in fact this lemma is a weaker version of a stronger theorem that basically states that this is an equality for the theta function. But for the purposes of our proof, we don't need the equality. We just need this inequality and that's all that we'll show. Good. So notice that theta of G for any graph G is a minimization problem, right? And I want to show that theta of G dot H is less than or equal to theta of G times theta of H. Right? So what we'll do is the proof strategy is as follows. So use the optimal orthonormal representation for G and an optimal orthonormal representation for H to give a valid orthonormal representation for G dot H. Okay, so this is going to be our proof strategy. Okay, and the value of this that because we are constructing it, right, the value that it will take will turn out to be the product of the two theta functions of G and H respectively. Okay, so let's go ahead and do this now. So again, let me write down the theorem just to keep it in mind. We want that the theta function of G dot H is less than or equal to the theta function of G times the theta function of, sorry. Oops. Sorry, I think if I write on top, it's having some issues. So let me just not do that. Okay, so this is what we want to show. Okay, so given, and let me take an optimal orthonormal representation for G and one for H. Okay, one that attains the theta function value. So recall that orthonormal representation is this vector assignment for every vertex such that it satisfies certain orthogonality constraints, and we have defined a value for that. So let me say that be an optimal OR for G. And notice that the value of this is minimized at some with some handle vector, right? If I'm going to call the handle vector for G to be C and let V1, V2 to V is W, B, or maybe I should just call it W1. Oh no, V is fine, yeah. For H, and the handle vector for this is different because there was some other minimizing handle vector. So let me call that handle vector D. Okay, and you might think that maybe the dimensions of these are in different spaces. What we do, that's fine. We'll just combine them somehow. So now using this, I want to come up with an orthonormal representation for the product G dot H. Okay. Now, what do you do intuitively, right? When you had the vertex set became a cross product, right, of the two. If you have these two sets of vectors, how do I come up? So let me call this vertex, say, so if I is a vertex in G and J is a vertex from H, so oops, I should avoid writing above. Right. So suppose I take I in B and J in W to be two vertices. Then the vertices in G dot H are these tuples I comma J, right? Okay. How do I define a vector for I comma j? Can someone give any suggestions? It has to do something with cross products, right? But in the vector world, what would you replace that by? So yeah, the suggestion came. Basically, you replace it by a tensor product, right? So now you take the tensor product of ui and vj. So this is the tensor product. And at least for finite dimensional spaces, the tensor product of x and y, where x in say R n and y is in Rm, is defined as just x1, y1, x1, y2, xi, yj, all the way until xn, yn. Okay, so all pairs ij appear over there, right? And this is in Rmn. You can think of it as some bilinear mapping, but I'll not do that. So this is concrete and nice. Good. So now what I can do is tensor product satisfies the following property, that notice that we have to deal with inner products, and I've taken tensors of vectors, right? A vertex in V of G dot H is has this representation ui cross vj, right? And now what we want to say is that, well, okay, what's the handle vector that I'll take in order to define the value of this? Maybe I'll state a property here that I'll actually use later. Okay, which is basically that if I have inner product of two vectors in this extended tensor space, okay, if I take the inner product of two vectors of this form, this is equal to x transpose y, sorry, dimension mismatch, x transpose x prime times, now this is a scalar, times y transpose y prime. Okay, and we are going to use this now. So the first thing you can do is you can say that you want to satisfy the orthogonality constraints. And why is that? Since, well, it comes from the definition of graph project. So if I have ui tensor vj transpose times, suppose I take ui prime tensor vj prime, right? This is what? By fact, this is ui transpose ui prime times vj transpose vj prime, right? And if either of them are not an edge, right, then this will be zero. This should be e bar f bar. Okay, but this is exactly the condition for um, ij to not have an edge between I prime j prime. Okay, so this is an orthonormal representation, right? It's easy to verify. The main thing is that this tensor product trick works, right? And we don't really restrict the dimensions in our representation, so that's fine. That's fine. So dimensions also match. Now, the second thing to show is what is the value of this orthonormal representation. So notice that, let me call this, did I name these sets? Okay, so let me call this, say, P, Q, right? The orthonormal representations for G and H. So what I will do is I'll look at the orthonormal representation of, I'm just calling it P tensor Q. Right, so P was the orthonormal representation for G, Q was the orthonormal representation for H. Okay, what is the value of P tensor Q? The first thing you should ask is the vectors are of the form, these are vectors of the form UI tensor Vj, right? These are the vectors in this set. I'm just defining it that way, right? Now, what should the handle vector be, right? And there's a natural candidate for choosing the handle vector. Which is basically the tensor product of the individual G and H's handle vectors in the optimal orthonormal representation. So using this, what happens? Oops, sorry. I get, so maybe there's a more optimal handle vector. I'm just not using it. And therefore you get an inequality of max over vertices. But vertices are I in V and J in W of 1 over, and let me write it like this first, C tensor D transpose UI tensor Vj, and this the whole squared, right? Maybe this is not clear here. Yet again, C tensor D is a candidate handle vector. Okay, it has norm 1. And I'm just using that and I'm upper bounding because you had a minimization over all possible handle vectors in the theta function of this orthonormal representation. And here's a candidate handle vector. So the theta function should only be lower. And this actually is equal to C transpose UI square using the fact D transpose Vj squared. And I can separate these out because this is going over all pairs I, J, and V cross W. Without any restriction. So, and each of this is actually, because this is optimal orthonormal representation, this is equal to theta of G times theta function of H. Okay. So this shows lemma A. It shows that the theta function is multiplicative. Okay. And from this is where we derive that theta function of G to the power K is less than equal to theta function of G times theta function of H. Any questions about this proof? Once you get the tensor product trick, it just works. Okay, it's just a matter of working it out.
So can we say something about when will the equality hold?
Right. So you're asking when will equality hold? So actually equality holds always. Okay. When you look at theta functions, it's just that here I'm only showing the inequality because that's all we need. Okay? You can actually go one step ahead and show that the theta function is exactly multiplicative, not like sub-multiplicative over here. That requires a proof. Given any solution to P tensor Q, uh, or given any orthonormal representation of G dot H, can you figure out orthonormal representations for G and H? Okay, that's one way to go about it. Okay. There are other ways also, which we will maybe discuss later. Okay, good. So I hope that clarifies. This finishes the proof of lemma A, which is that theta function is multiplicative. And now that we show theta function has some nice property, now the question is, can you lower bound it by relating it to the quantity that we wanted? Right. So let's do this now. So this for any graph G, let U1 to U1 be an optimal orthonormal representation for G prime. And let me say the handle vector that caused the optimum is C. And now what are we going to do from this? We are going to somehow relate it to the size of the independent set. Now, how do we do that? Okay. So let I be an independent set in G prime. Okay. Now, what do I know about I? Right. So I is the set of vertices in G prime, no two of which share an edge. There may be edges outside, but none to each other. Right. So this is an independent set I. There are other vertices in the graph. Now, one nice property is that if you just restrict your attention to the vectors that the independent set vertices are being assigned, right? What do they look like? Right? They will look like the standard basis, right? They're all mutually orthonormal, right? And therefore, for the handle vector C, I claim the following, right? The norm of C, which is basically C transpose C, is at least the sum of squared of projections onto these vectors because they're all mutually orthonormal. Okay. Do you see why this is true? Just because they're all mutually orthonormal, right? So they are like standard basis for a subspace of whatever the dimension R and say. And therefore, if you project C on these, look at C in this basis extended, then the norm 2 norms square of C is at least summation I in I C transpose UI squared. Okay. But I know that C is a unit vector. The handle vector is a unit vector to begin with. This implies that 1, which is basically norm C squared, is greater than equal to, and now maybe I will do this translation over here itself. Let me write it again. And this is greater than equal to. Now I'll bounding this sum by the minimum, right? I can always do that. Right? So notice what I've done. I've replaced all of these terms by the minimum into the number of terms. It's surely greater than equal to. Right? It's a simple trick, but what it helps us in doing is it gets us this size of I outside. And now you see the proof is done because I'll just transpose this down. Mod I. Okay. To be more concrete, I need not do this quite frankly, but so let I be a maximum independent set in G, in which case this is alpha of G. So I can switch the maximum to a minimum to a maximum, sorry, I'm just changing it to the numerator. And this in turn is at most maximum over all vertices. Here I'm going only over vertices in the independent set until now. I'll just expand it to everything. Okay, and notice that this last thing is nothing but theta of G prime. Okay, so what I've shown is that alpha of G prime is less than equal to theta of G prime as promised. Okay. So good. So I've proven both my lemmas, and this gives a complete proof of Lovasz bound that S of G is at most theta of G. Okay, we have completed the proof of this. Now let's go ahead and see what do we do with C5. I have around 15 minutes, and this will be correct time to actually go into what happens for C5. Okay. So let me write it in big terms here. What we have is S of G and this is nothing but alpha of G to the K raised to 1 over K. So this is my theta bound. No, sorry. And let's go and see how we can use this on C5. Okay. Now here's the lemma. I claim that C5 has an orthonormal representation with value square root 5. Okay, and therefore the theta value of C5 is exactly equal to square root. Okay, that's just, this is trivial. But more importantly, recall that we had shown that S of C5 was greater than equal to square root 5, right? I hope you remember this, that when we take the second power of C5, right, when you set K equal to 2, so why is this true? We looked at alpha of C5 squared, and we are kind of brute forced our way into showing that, alpha of C5 squared is actually equal to 5, right? And this implies that alpha of C5 squared to the power half root 5, and this is, and S of C5 is the supremum over all K, right? And therefore, S of C5 is greater than equal to root 5. So this we had shown before, and we had actually listed down what is the, it was just you take the second power and find 5 vertices such that it forms an independent set. That's basically what we had done. But now, since S of C5 is upper bounded by theta function, which has value square root 5 for C5, what do we get? We get that actually it is equal to it is equal to square root 5. And this is Lovasz's favorite result, famous result. Now, we had seen some trivial examples of orthonormal representations for the complete graph or disconnected graph, maybe some slightly non-trivial ones for C4, but then what can you come up with for C5? Right? We want an orthonormal representation for C5, which is basically this graph. If I label it 1, oops, 3, 4, and 5, I want a set of unit vectors for every vertex such that the following orthonormalities hold. 1 is perpendicular to 3, 3 is perpendicular to 5, and 5 is perpendicular to 2. Yeah, so all of these orthonormalities, I've put more than what I said. All of these orthonormalities should hold. Right? 1 should be perpendicular to 4 and 3, and 2 should be perpendicular to 4 and 5. I think the rest is implied by these. So how do I come up with a non-trivial orthonormal representation that magically seems to attain the square root 5 value. So let us go back to that intuition. So here's C5. Right? And the goal is to come up with one orthonormal representation for it, which is efficient. So come back to that efficient idea. That is, the value should be small. And we had said that intuitively the value is small if the following happens. This is an orthonormal representation. If the vectors kind of cluster around the handle vector. Okay, so this was our intuitive idea that I had given um, for the value being small of an orthonormal representation. So you had this handle vector C, and all the other orthonormal vectors are kind of like this. So let's try to find such a representation. Okay. So let's start off with something. Okay. So suppose this is my two-dimensional plane here, the plane of drawing. See, and I'll first fix the handle vector to be perpendicular to the plane. Okay, that is coming out of the paper. Okay. So when I see it like this from the top, I just see a point, C. Okay. Now, I suppose I label the vertices 1, 2, 3, 4, and 5, right? Now imagine the following. I start off with a set of vectors that is not an orthonormal representation, okay? But it's a natural one. It's along the edges of a unit pentagon, right? A regular pentagon. So this is U1, this is U2, exactly what is there, U3, U4, and U5. Right, so this is the set of vectors that I start off with. They're all of equal length and they are the edges. They are the vertices of a regular pentagon on the plane of the drawing. Okay. Now what do I do? Well, first I see, well, what are the orthogonality constraints I want? I want U1 to be orthogonal to U3, and the others are all symmetric, U1, U3, U1, U4, U2, U5, U2, U4, right? These are these kind of orthogonality constraints I want. Now, what is the angle between U1 and U3 in this picture? The angle between two adjacent vectors here is 2 pi by 5. So the angle between U1 and U3 is what? Is 4 pi by 5. Notice that this is greater than pi by 2, which is orthogonal, right? So they're more spread out than needed in this position. Okay. Now imagine that this is an umbrella, okay, or the spokes of an umbrella that is fully open. Somehow the umbrella is completely flat. And now I pull the umbrella down to kind of close it. Okay, I hold the handle, that's why the name handle vector, and I pull the umbrella to close it. So all of these spokes, they start collapsing down, and in the final position, the umbrella is completely closed. I'm just drawing C now in the plane of the paper, it's perpendicular, but yeah, and when the umbrella is closed, all the vectors U1, U2, U3, U4, U5, all of them lie along C. Okay, and therefore the angle between them is 0, right? And this is the kind of the open umbrella. Okay. So the angle between the vectors that I wanted orthogonal in this continuous process of closing the umbrella has gone from 4 pi by 5, which was larger than pi by 2, to 0. Right? That means there should be some intermediate stage at which the angle between u1 and u3 hit pi by 2. Right? And because this is a symmetric instance, the angle between u1 and u1 and u3 is going to be the same as the angle between u2 and u4, and the angle between u1 and u4, and so on. Right? So the observation, at some intermediate point, orthonormality is satisfied. Right? And now all that requires us to do is figure out what is this intermediate point. It will be some intermediate point where basically it's going to look, and I have a picture on the next slide, so I'll switch to that. You started off at this, and at some intermediate point, right? This was u1, u2, u3. The angle between say u1 and u4, this became pi by 2. Right? And this is that intermediate point. Right? I just need to determine the coordinates of the vectors at this point and figure out what the value of this orthonormal representation is. Okay. I'm not claiming it's optimal, but let's work it out because this seems like a really natural one. Okay. So if you work out the vectors here, when it satisfies the orthonormality condition, will satisfy the following. Each ui, so at the satisfying point of being an orthonormal representation, vector ui can be described by the following. So I is the index I here. Maybe I'll put it. Yeah, that's fine. I hope that's fine. Okay, and then there's some third coordinate. This is in 3 dimensions. Okay, so if you look at the projection on the spokes plane, it will have certain coordinates, and then there's a z coordinate also. We have not determined z yet, but it turns out that actually if you work this out at this point using these coordinates, you'll get a value of z. Let me just write it. Uh, so u2 transpose u5 should be equal to 0, and therefore this implies what do I put u2? Yeah. So if you put I equal to 5, you get cos 2 pi and sin 2 pi, right? So that becomes just 1, 0, z. This may be rated u5 transpose times. So this implies, if you just simplify this, you'll get an equation cos 4 pi by 5 plus, etc. This is just typical working out. Right, so you get a value of z. And once you get this value of z, you can actually compute the value of this. And it turns out that the value of this orthonormal representation actually turns out to be something like 1 minus cos phi by root 5. Okay, so almost magically, it turns out to be square root 5. Okay. And this shows that the value of the Shannon capacity, or 2 to the power Shannon capacity, um, which is basically S of G for C phi, is equal to square root 5. Okay, because the value of the orthonormal representation is square root 5, and we had shown that it should be at least square root 5. So then it has to be. So any questions about this? This is a really nice, really clever construction. and kind of magically gives us the optimum value. There's no reason that this construction should give us the optimum, but it magically does. Okay, so I'm almost out of time, but I'm almost also finished what I wanted to mainly cover over here. Um, that is, the key ideas at this point that we have used are that to analyze Shannon capacity, you use the proxy theta of g. Okay, why did we use this theta of g? That's because Shannon capacity dealt with independent set in products graphs, right? This is hard to analyze. Whereas here, this function is easy to analyze on product graphs. In fact, it's equal, right? And therefore, we use this proxy and analyze this proxy, and therefore we got a bound. And in the case of C5, this was optimal. Okay, so multiple questions that you can ask at this point, right? So theta of g is finally a bound on the Shannon capacity in some way, right? But is this tight? Is the Shannon capacity actually equal to theta of g for graphs, for all graphs? Okay, or for what graphs does it actually turn out to be equal? Okay, so these are the kind of questions that we'll discuss more in tomorrow's lecture. How does Shannon capacity actually relate to the theta function, and also the further ramifications of such a definition of this. Turns out that this is quite prescient, and it has a lot of applications in the design of approximation algorithms. Not just particularly this, but the principle behind relaxing S of g to this function theta of g and analyzing theta of g. Okay, so we'll discuss semi-definite programs, the relation to Lovasz theta number, and more approximation algorithms. Okay, and you'll see, hopefully see a common thread among all of this. So I'm almost out of time, so I'll stop here for questions if people have any. I'm happy to answer them.
The questions?
Yeah.
Okay. Stop recording.